Okay, so we were talking about Lvalues, Rvalues, and stuff like that, so-called value categories in the last lecture. So I'm going to be continuing on talking about this today. We just finished talking about going through some examples of various different things that would constitute L-value expressions. So I'm going to continue on that theme for this slide. So again, some of the kind of more important things are marked with stars. Some of this is a little bit more information than really what you need, but some things are kind of more important types of L-value expressions than others. So an R-value expression, or R-value reference to a function is an example of an L-value expression. This is probably a less common thing to occur. At least I don't think you'll probably have this in any of the code that you write for this course, but the situation can arise. So we have this is an R-value reference to a function. This is being bound to a function here, so this would be an example of something which is an L value here. The next bullet actually is a more kind of practically useful thing, or more commonly occurring sort of thing that you might care more about. Most built-in operators tend to yield R-value expressions, like maybe you have two integers or something. You're adding like a plus b or something like this. Most of them tend to give R-value expressions, as we'll see later. But there's a few notable exceptions, which are basically these ones here. So the subscripting operator, the built-in subscripting operator always yields a L-value expression, except when maybe the array that's being indexed is a temporary object or something like that. So like in most cases that we're going to be interested in, it's going to be an L-value expression. The built-in indirection operator, like star when you dereference a pointer, this yields an L value. The pre-increment and pre-decrement operators, so like plus plus before the thing that you're, the variable you're incrementing or decrementing, these correspond to L value expressions. Also, any kind of assignment thing, assignment or compound assignment, these also yield L value expressions. So just to walk through some examples to illustrate some of these points here. So star is the indirection operator. So if I say star s, this is an example of an L value. Or star s plus 1, so s is a pointer. I'm going to that pointer, going one further in memory by adding 1 to it and then dereferencing what's there. So star s plus 1 is an L value. Plus plus s is an L value because I'm applying the pre-increment operator to s. Pre-decrement operator I'm applying to s. Also, this yields an L value. I can also do things like compound assignment, like plus equals. This is what's referred to as compound assignment. You're combining some operation with assignment. So it's called compound assignment. So this s plus equal 2 is an L value expression. In this expression here, where we take the address of a buffer up above here, and then the address of buffer 1, so we're indexing one element into this buffer above, taking the address of that element and then assigning to s. This whole line, up to the semicolon, this is an L value expression. Also buffer bracket 1 end bracket, this is also an L value expression as well because it's the result of the subscripting operator. This gives you some idea about what I mean by some of the points up above. With respect to moving, because the main reason in which or context in which we're concerned with L values and R values in this course is with respect to things that relate to moving versus copying and so on. So if we have an object that is referred to by an L value expression, because again, although we're talking more generally about expressions, when we're talking about moving and copying, we're talking about objects. So what we're really interested in, we have an expression that refers to an object, and we're concerned whether that expression is an L value expression or not an L value expression, what we call an R value expression. So kind of the bottom line is, if you have a situation where you're copying from one object to another, and the source for the copy is an L value expression, generally, it's not safe to replace the copy with a move, unless you have much more detailed knowledge about what's going on in the code. You can't kind of categorically say it's safe, or maybe wording in another way, what's on the slide, it says it's not guaranteed to be safe. So because of this, the compiler will never, in a situation where you're moving from something and that something is an L value expression, the compiler will never use a move because it might not be safe to do so. And the compiler will always err on the side of being conservative because it doesn't want to do something that might cause a bug in your code. It will only make transformations to your code that it knows for sure are correct. And the reason why L values present problems, L values have identities. They have well-defined locations in memory where they reside. So there's lots of parts of the code that could potentially be observing the value of a variable that's an L value. And if you just go in and say, I'm just going to change the value to something else, lots of code could potentially be, unexpectedly using the wrong value for a variable suddenly. Maybe to further illustrate this, I have a code example here. So We have like a vector of int called x, and then we're creating another vector of int called y that's being constructed from x. So this would either be using a copy or a move here, basically propagating the value from x to y. And the question becomes, well, would it be safe to use a move instead of a copy here? If we look at this line in isolation, like we don't consider other parts of the code, and this is what the compiler does. The compiler never tries to consider other parts of the code and try to really think hard about things. It just looks at what's here and says, can I categorically say by looking at this expression it's safe to move? And the conclusion it will come to is no. And the problem here is if it did do a move, you're going to obliterate the value of x potentially, right? If x has its value obliterated, because x is an L value, it's like a named object here. Because of this, there could be code down below that uses the value of x, but you just nuked it. So like, good luck with that. I mean, what your code's going to do down below is going to be do really weird things because it doesn't expect the value to be mangled. So this is the sort of issues that revolve around L value expressions. There are typically, you have a named object, you can refer to it by name, and you might observe the value that's been mutilated. Or also someone else might have a pointer to it or something like that, some other part of the code. And if you change the value, it's not going to know that it's going to be changed, and then it's going to do the wrong thing. So for this reason, this would always be using a copy type operation. And then we have like assignment as well. This is construction. We also have a similar problem with assignment. So I'm assigning x to y. Should this use a copy or should this use a move? When the compiler looks at this, when it makes this consideration, it only considers this line in isolation. So it says like, can I categorically change this a potential copy into a move? And the conclusion it comes to here is because the source for the copy is an L value expression. In this case, it's a named object. A named object, if you remember, is an example of an L value expression. Because of this, the compiler will not change the copy to a move because it might be dangerous to do. The bottom line is there could be code down below here where the ... is, where it uses the value of x, expecting its value not to be mutilated. But if the compiler just secretly inserts a move here, now the value of x is mutilated and your code does the wrong thing. Also, other parts of the code maybe have a pointer to that variable somehow, and things won't work out very well. So again, L values are not move friendly, I guess is one way to put it. Any questions? Okay, so that's L values. And things that aren't L values are what we call R values. And there's two categories, subcategories of R values, what are called pure R values, PR values up here, and then what are called X values, which stands for expiring value. So what are these things? Because we have to kind of be a little bit more specific because we're trying to kind of carve up R values into two subcategories. So a pure R value is an expression whose evaluation either computes the value of an operand of an operator or it initializes an object or a bit field. You can ignore the bit field part in this course because we're not going to be using bit fields. And probably the second bullet is the more important one. It's basically used to initialize an object. It's not an object by itself, but it can be used to initialize an object. And I'll go through some examples on the subsequent slides to kind of further elaborate on what I mean by this. Pure R value expressions, they never refer to an object. Again, they can be used, there are things that can be used to initialize an object, but they are never themselves objects, at least not in current versions of the standard. Old versions of the standard, things may be a bit different, but again, this is one of the nice things about being in academia. C++ didn't exist before C++ 17, so I'm just going to talk about C++ 17. There's no such thing as legacy. Pure R values, they don't have an identity. We talked about the notion of identity before. Like all pure R values that kind of are spelled the same way in your code, they're all the same thing. You can't distinguish between them. Like 4.2, it turns out the literal 4.2 is an example of a pure R value. It doesn't have any identity. Any 4.2 that appears in your code is the same 4.2. You can't distinguish between one 4.2 somewhere in your code and another 4.2. So that's kind of the short story about pure R values. I'll go through some examples on subsequent slides. Then we have another subcategory of R values, which is what's called an X value or expiring value. And basically, this is very much like an L value, except kind of with one minor tweak. Well, actually, I mean, there's two. One is kind of a less important one. The word function is omitted here, so it can't denote a function. Functions aren't X values. But we're interested in objects with respect to copying and moving. So in this sense, there's not really any difference with L value. If you go back and look at the earlier definition, it says denotes an object, function, or bit field. So that's basically the same modulo the function. Has an identity. This is also the same as the definition of an L value. The difference is in the third bullet. This is the important thing. An X value, it's safe to do a move from. Essentially, what it is really is an L value where you stepped in and said, well, no, trust me, it's safe to actually move from this thing. So this is what an X value is essentially. Otherwise, it's very similar to an L value. X values are associated with things like when you create a temporary object, often these are associated with X value type expressions. And then simply an R value, as I mentioned before, an R value is any expression that's either a pure R value or an X value. So these two things combined collectively are what we call R values. And with respect to copying and moving, really all we care about is whether something is an L value or an R value. That's good enough to figure out whether a copy or move happens. The only reason I'm splitting hairs and breaking down R values into these two subcategories of X values and pure R values, another thing I want to talk about is something called copy elision. And to understand copy elision, you need to split hairs and talk, because you need to know what a pure R value is, essentially. Otherwise, I can't kind of fully talk about copy elision. But from the point of view of moving versus copying, all we really care about is it an L value or an R value. We don't have to split hairs and say what type of R value it is. But I'm introducing these X values and pure R values because we'll need them later. Anyway, just to give you some idea about where we're going. Unlike L value expressions, R values need not have an identity. Well, basically pure R values, for example, don't. Also, because they don't have an identity, don't necessarily have an identity, you can't take the address of an R value expression. If you use ampersand, like the address of operator, and apply it to an R value expression, the compiler will probably give you some message that before today you never would have understood. They'll probably say something like L value expression expected when you're taking the address of. Now you know what it means. It's telling you you can't use an R value expression, which again makes sense. R value, because R values don't have identities, they don't have well-defined locations in memory. It doesn't make sense to take the address of it because maybe it doesn't even have an address in memory. Maybe it just resides temporarily in some register or something. Anyway, enough about R values. So let's go into some examples of pure R values and X values. So again, these are subcategories of R values. So pure R values, maybe one of the most important ones is a function, a result of a function that returns by value is a pure R value expression. So for example, if I have a function called get underscore value, it's returning, the important thing here is not that it's returning an int, but it's not returning a reference type. It's returning by value. The expression get value bracket bracket, or I guess I should say parentheses parentheses, this is a pure R value expression. Notice that get underscore value without the parentheses is quite a different animal from get value with the parentheses. Without the parentheses, it's just the name of a function. The name of a function, it's a named thing. It's an L value. But when you put the brackets in, it's then the return value of a function that returns by value. This is a pure R value expression. So it does matter whether we're talking about this thing with the parentheses or without the parentheses. Anyway, and this is maybe one of the most common sort of situations for pure R values because there's lots of functions you have in your code that return by value. And basically, those expressions are all going to correspond to pure R values. Another very, very commonly occurring example of pure R value are literals. Any literals that are not string literals, we saw before string literals are examples of L value expressions. Every other literal type in the language is a pure R value. So for example, 3.1415 is a pure R value. 4.2, this is another literal, a literal of type int. We have like a literal of type int here, 2, another literal of type int here, 1. A, which is a character literal. So these are all pure R value expressions. All of these things can be used to initialize objects, right? This is one of the properties of pure R values is they can be used as initializer for an object. So I can certainly initialize a char with quote A, and so on. The this keyword as well, when you're writing classes, I mean, often you don't write out this. I notice in some assignments, people are writing out this, like in their solution. Normally, people don't write out this unless there's some ambiguity that would be introduced if you don't write out the this keyword. So normally, you just refer to data members by their names without the this in front of it. Anyway, but if you do write it out, I mean, this is a PR value. In other words, there's not any well-defined position in memory where this is stored. The thing it points to, there's a well-defined location for the object, but this itself is this nebulous thing that we don't really know where it is. Maybe it's just a register or something. It's an example of a pure R value. So you might not write this out very many times in your code, but anytime you're writing a class, it's baked into what you're doing. So this kind of implicitly is used quite a lot. So those are some examples of pure R values. The last category of things that I want to talk about are most operators in the language, built-in operators. So like, things like post-increment, post-decrement, all the arithmetic operations like addition, subtraction, multiplication, division, modulus, things like this. Bitwise operators like bitwise and or, exclusive or, things like that. Logical operators and or, and so on. Relational operators, less than, greater than, things like that. And the built-in address of operator, all of these things yield pure R value expressions. So in some sense, maybe statistically speaking, most things probably tend to be pure R values in your code. because we have a lot of things like that look like what shows up in this example here. So for example, on this line here, 3 by itself is a pure R value, 5 by itself is a pure R value, 3 plus 5, because it's the result of a built-in operation, a binary addition for int. 3 plus 5 is also a pure R value. Even if I throw in the minus sign here, minus bracket 3 plus 5, this is also a pure R value because I'm doing like another arithmetic operation, unary minus, and so on. It's a whole bunch of things like testing for equality. This is also this expression here. The result of testing for equality is a pure R value. So I equal 42 is a pure R value. This is an example like a bitwise operation. We're doing I and 7. So like a bitwise AND operation, the result of I and 7 is a pure R value. Here we have post increment. This is J++ is a pure R value. And here we're taking the address of I. The address of I is a pure R value. Any questions? Yeah?
So string literals are not PR values.
Right,
so
they're lvalues.
They're lvalues.
Which sort of makes sense, right? Because what's kind of the essence of an lvalue? It's something that has a well-defined location in memory. If you think about how the compiler is going to implement a character string, it's going to stick those characters into an array somewhere in memory. Like it'd be kind of hard if it didn't store them somewhere, because the strings can be quite long, and it could be quite much longer than any register on any processor. So it kind of makes sense that it would need to store it somewhere in memory. And the language kind of specifies, yes, it has a well-defined address. But in the case of literals, like something like 3, it doesn't really need to store 3 in memory to remember what 3 is. It just is what it is. Like there's not any compelling reason why you would need to store it in memory. Whereas a character array, string literal is different because it could be quite long, and you might need to store it in memory to make sure you can remember what its value is.
So could you get the address then of a string literal?
Yeah, you can take the address of a string literal. Yeah, that's a valid thing to do. But you couldn't take the address if I said like &3. I can't do that because 3 is not an L value. Yeah. Any other questions? Yep.
So is the variable itself an L value, but then the right hand side what you're saying is R value?
Okay, so like you mean like I here, for example?
Yeah,
Okay, so I is a named object. If you remember from the earlier lecture, actually that's maybe the kind of classic example of an L value expression. A named object is an example of an L value expression, which sort of makes sense, right? Because I am referring, like I can access the variable I through its name, so it must have some well-defined place in memory where I can access, otherwise how's it going to remember what I is? So yeah, a named object is always an L value expression, but if I put an ampersand in front of it, then ampersand I is the result that's produced from the address of operator applied to I. And the way it's defined in the language, the address of operator yields a pure R value expression. That answer your question? Okay. Any other questions? I mean, admittedly, this is kind of gross. And if C++ didn't have to have all it, like it's trying to remain backward compatible. Like there's a lot of things in the language. If you look at it today, and you say, well, this is just disgusting. Like, why does it do things this way? It's kind of insanely complicated. If you wanted to be kind of very negative, you could just try to blame the standards committee, but it's not really their fault. Like they're trying very hard to remain backward compatible, and don't underestimate how hard it is to keep adding new features to a language, but make sure that all of the hundreds of millions of lines of code that are out there that have been written over the last 30 years or so, they all still compile and work the same way as before. It's very hard to do. So a lot of this grossness, there was no, well, C doesn't have any notion of some of the stuff that we're talking about, like moving and copying. This is not a thing in C. And it was only basically added since we moved towards C++. So we're trying to remain backward compatible with C, but still have these new things. This is what leads to a lot of this grossness. But unfortunately, it's grossness that we really have to deal with if we care about efficient code, because you can't understand moving versus copying unless you understand the difference between L values and R values. And also, you can't understand copy elision, which is essentially an optimization that allows you to get rid of the copy and move altogether. Like, what's better than copying while moving? What's better than moving? Don't do anything at all. So this is the other thing I want to look at. Copy elision is really important because it's kind of the holy grail. It's like we just don't do anything at all. That's better than any kind of optimization you can do. But unfortunately, to understand that, you also need to understand kind of the nitty-gritty, the pure R values versus kind of other types of R values and so on. Anyway, so it's all kind of gross, and I admit it, but you still need to learn this stuff in the course because it's important with respect to what we're doing. Yeah, enough about that. So that's pure R values. The other kind of subcategory of R values are what are called X values. And there's kind of less things that lead to X value type expressions. One of them is if you have a function, the result of a function, and the return type of the function is an R-value reference type. So in this case, well, I guess you can't really see here from the definition of this function, it's not shown, but std_move returns like a double ampersand kind of type. It returns an R-value reference. Something like, for example, a type maybe that looks something like, say, std string ampersand ampersand. This is an R-value reference to a string. This is actually what in this particular case here, it turns out this is what std_move returns. It basically returns the type of this thing, which is a string from up above, but it adds a double ampersand. It's basically a typecast operation. A typecast makes it into an R-value reference type. So because of this, because this function returns an R-value reference type, std_move of s is an X value. Another example, which is almost sort of like this one up above here, anytime you have an unnamed R-value reference, which is sort of what we have here, the std_move of s, it doesn't have a name, it's just a temporary object, the return value of the function. Anytime you have an unnamed R-value reference to an object, this is also an X-value expression. It turns out that std_move actually is just basically doing a static pass. It doesn't move anything. It doesn't even probably generate any CPU instructions in your code. It's just casting the type of something to add an R-value reference to it. Anyway, so this is an X-value expression. If we do something like static pass, std string ampersand ampersand s, we're basically forcing s to have the type R-value reference to a string, but it doesn't have a name because this right-hand side has no name. It's just a temporary object that's on the right-hand side of the equal sign that's holding the result of the static pass. It's unnamed, therefore this is going to be an X-value expression. The other one, which is actually quite an important one, a temporary object that's created from a pure R value, because often pure R values in your code, what ends up happening to them is they're used to create temporary objects. So remember, pure R values, well, there's a few things they do, but one thing that they do, they can be used to initialize objects. So often what you have is an expression that's used to initialize a temporary object. And when that temporary object gets created, what you have now is an X value. The actual temporary objects that are created from, for example, from pure R value expressions are X values. So just to give an example of this in the code here we have a vector of ints called v, and then we're assigning to v here std vector int 10(2). So this right-hand side of the equal sign, this corresponds to, this is essentially going to cause a temporary object to be created that holds a vector with 10 elements in it that are initialized to 2. This is a constructor which will create, the first parameter to the constructor is the number of elements. The second one is the value that the elements are all initialized to. So we'll create this vector of 10 ints, all initialized to 2. It's sitting here in this temporary object, and this right-hand side here, this expression corresponds to an X-value expression. The temporary object that is, the fancy wording is materialized, but the more normal speak is probably if it's created. But in the standardese, they have to introduce lots of impressive words. So we say materialized, but essentially it's saying we created a temporary object. So this corresponds to, again, an X-value expression, this right-hand side here. But before the temporary object is created, that expression is a pure R value. So it's kind of complicated to say exactly what this right-hand side is. It's like the most correct way to word it is that this std vector int 10(2), it's a pure R value expression. It's an expression that can be used to initialize an object. But then this line of code is going to force a temporary object to be created. And once that temporary object is created, the temporary object itself is an X value. So this line, depending on how you want to view it, from what point of view, you could sort of say it's a pure R value, but also it's kind of an X value, but that's slightly different points in time. The X value is the temporary that's been created. The pure R value is the expression from which the temporary is created. I hope that makes some sense. Anyway, this is admittedly kind of complicated stuff, but you'll get better at things as you kind of go through and look at more code and are asked to identify whether things are pure R values or X values and so on. Yeah, I think that's all I want to say about this slide. So again, moving is sort of the theme here. This is, at least at this particular point in time, the main focus of why I'm introducing Lvalues and Rvalues is with respect to moving and copying and when do we move versus when do we copy and so on. So we talked about moving in Lvalues. Lvalues are bad news for moving. Basically, the compiler is not going to move because it can't say categorically it's a safe thing to do. Rvalues are the opposite, though. If you have a source for a copy operation that's an R value expression, it's always categorically safe to replace the copy with a move. Essentially because if you have an R value expression, if we kind of ignore the slicing and dicing of things into X values and pure R values, with respect to moving, all we really have to care about is whether something's an R value. It doesn't matter whether it's X or PR, just R value is good enough. R values, the thing that's special about them, R values either correspond to temporary objects. If there are value expressions that correspond to objects, either they correspond to a temporary object or they correspond to something that the programmer has said, treat this as a temporary object. In other words, they've introduced typecasts into their code to play games with the type system and the language to say, hey, treat this as if it's safe to move from. I don't care whether you think it is or not, just do it. And the two examples that I have on this side sort of help to illustrate this. The reason why it's safe to move from a temporary object is that temporary objects have no name. Remember, one of the defining properties of a temporary object that's introduced by the compiler, it has no name. And what you have to think about is if something mangles the value of a variable, if you replace a copy with a move, and then as a result of doing the move, you mangle the source of the move operation, how can that have a negative impact? The only way it can negatively impact your code is if some part of the code looks at that value, observes that mangled value, and then doesn't realize it's been mangled and goes on in blissful ignorance, uses the value, and bad things happen. So you have to have that the variable can be observed by some other part of the code so that it actually can do something wrong. The thing that's special thing about temporary objects is that it's impossible for anyone else to observe the value having been mangled. And maybe this can be illustrated by way of a simple example here. So here we have a function called func. It has this vector of ints called x, and then inside the function here, we're initializing x to this vector of 42 zeros. Again, the first parameter here is the number of elements, and then 0 is the value for each element in the array. And then somewhere down, and what we're trying to say here is it safe to replace this copy with a move? In other words, can I move from this temporary object here into x? The rules of the language basically say, like, as far as the compiler is concerned, it looks at this right-hand side of the equal sign expression here and goes, is this an L value or an R value? It looks at it and says, this is a pure R value expression. It's an expression that can be used to initialize an object. It's not an object itself, right? Std vector, blah, blah, blah. This is not an object, but we can use it to initialize an object. Therefore, it's what we call a pure R value. But more generally, it's an R value. All we really care about is it's an R value. So the compiler says it's safe to do a move here. But why is it safe to do a move here? If we kind of forget about what the compiler's thinking, all this fancy stuff about R values, L values, like why is it safe to move here fundamentally? Well, if we move here, then probably what's going to happen is after we do the move, the value of this temporary object is going to be completely mutilated. Its value is going to be some other thing. In practice, probably what will happen is it'll be an empty container. What will happen is you'll rip the guts out of the temporary object, put it into the container X, and then the temporary object will probably be empty. But anyway, it doesn't really matter what's happening to the container, but most likely in a situation like this, it will mangle the value of the container. It won't be the same as before. But how could this cause any problems? Well, it only could cause problems if some other part of the code could look at this temporary object and actually use this mangled value. But the question is, like, how could it do this? And the answer is, well, it can't, because to access the value of this object here, well, how can you access the value of a variable? Well, it has a name. If it has a name, you can say, like, x, give me x, compiler. Well, temporary objects don't have a name. So you can't say, give me, you stop there. You don't tell the compiler what to give you. It can't give you the value of the variable, right? So you can't access it through a name. Also, it turns out, as we talked about kind of briefly a little bit earlier, R value expressions, you can't take their address. Because you might say, well, wait a minute, I can't access this thing by its name, but I can take the address of it, and then I can dereference the pointer that I get and see what it's there. But you can't take the address of an R value. So we also can't use the sneaky trick of, well, let's try to access things through a pointer. You can't, because you can never get the pointer in the first place. So basically what we have is a situation where it's impossible for anyone to observe the mangled value that results from doing a move. And it's not just in this specific case I'm showing as an example, but generally with temporary objects, no one will ever be able to observe the mangled value. So it's always categorically safe to replace a copy with a move, because there's no other code that could be negatively impacted, because no one else can ever see that changed value. So this is what makes temporary objects very special. Anyway, so in this case, we could replace the copy with a move. And in fact, this is what the compiler would do. We can also do other things. Because, like, what happens if we have more knowledge about the code than the compiler? And even though the compiler would do a copy rather than a move, what happens if we want to just step in and say, I don't care what you think, compiler, I want you to do a move here? Of course, with C++ being big on efficiency, we want to be able to take full control if we want, shoot off your foot if you like, but we have the gun, so we can do what we want. Of course, you don't really want to shoot off your foot, but the language is very powerful, and with that power comes great responsibility not to do stupid things. But in this particular case, what we have here is a situation where the programmer is going to override the default behavior in the language. I need to kind of say a little bit more about the code to introduce it and set it up. So here we have a string s, which is initialized to some value. It's not so important. Then we print out the value of s to the standard output stream. And then what we're going to do is we're going to create a new object, another string object called t. And we want to do this by moving s into t. Like we're actually going to force a move to happen. If I leave std move out here, if I just said t open parentheses, no std move, it's deleted. And I just have s close bracket, or sorry, closing parentheses. This is not going to do a move, right? Because if I just had like the no std move here, but I just had s appearing in parentheses, s is a named object. Named objects are lvalues. And lvalues, the compiler will say, well, yeah, it's an lvalue. Someone else might be able to look at this object. If I change it, it's not safe to replace the copy with a move. So if we just had an s here and this std move was not here, the compiler will do a copy. And the compiler doesn't look at any other part of the code. Like it literally just is looking at this expression here. It doesn't say, well, what comes later in the code down below here, etc. But we're smarter than the compiler in this case, or at least potentially we can be. We can look at the rest of the code in this function and we can say, well, clearly I never use the value of s again. I mean, it's not hard to do here because there's only one more line of code if you ignore all the comments. Clearly s is not used down here. So if we change its value, completely mangle it, who cares? It doesn't matter because there's not any possibility it can be used by anyone else. And because it's a local variable, like s is a local variable of this function, no one outside of the function could use it either. So we can say it's very safe, it's completely safe to do a move. But the language won't do it by default. But what we can do is we can force it to happen by using std move. Again, std move doesn't do anything. It won't generate any code. Essentially, all it does is play games with the type system. It casts, it's a template function. And what it does is it looks at the type of the thing that you're passing. In this case, s is going to be a std string. And what it does is it casts it to a std string ref, ampersand, ampersand. It casts it to an R value reference to the same type of thing. But then what we have here is an R value, like a return value of a function that returns an R value reference type. And if you remember from just a few slides ago, this is an example of something which is an R value. So basically all std move does here is it takes the thing in the brackets there, the s, and says, treat it as if it was an R value. It's an L value, S is an L value, but I want you to convert it to something that's an R value expression so a move will happen. So this is exactly what this is for. And this is why it's called std move, because the only sensible reason that you would use std move in your code, you could probably think of other bizarre things to use it for that don't make any sense, but the only thing that really makes sense to use it for is a situation where a copy would normally be done. You want to override that and say, no, I want to move. And when you do this effectively, what you're doing is saying what I've written down here. Trust me, compiler, I know more than you do. It's safe to move here, really. But the thing is, of course, if you're wrong, if it's not safe to move, you've just introduced probably a very serious bug into your code. So you have to be very careful once you start using std move, because there's a reason why the compiler has this kind of very conservative default behavior of not always doing moves everywhere, because it won't make things go wrong. It won't break things. But if you start putting moves in lots of places, you better be sure that it's safe to put them there. Anyway, but in this case, it's clearly safe to do, because once we mangle the value of s by doing this move operation, there's nowhere down below here where we're relying on that value of s. So it's categorically a safe thing to do in this case. But if instead we were doing some stuff down here where we're using the value of s without first assigning some new value to it, then we're using something that we don't really know what it is, and probably our code's going to break. Any questions? Yeah?
So does the original string s get cast to an x value in this case?
So essentially, well, so std move of s is kind of more generally, it's an R value, but the specific flavor of R value that it is, this would correspond to an X value. This was, I think if we back up a few slides here. Where is it here? This is this kind of example here. So this is like a function whose return type is an R value reference type. So like, if you look at the definition of std move, it's a template function, and all it does is it takes whatever type is being passed in here. This is, for example, a std string being passed in, because s is a std string, and it converts it to that same type, but with double ampersand. So it converts it into an R value reference to that thing. So because of this is an X value, which is, if I understood what you're saying is correct. You basically were saying, is this thing here an X value expression, std move of s? Yes, it is, for the reason it's effectively defined that way. Okay. Any other questions? Okay, so let's keep on going. I'm going to skip over that slide. So the top part of the slide is just kind of summarizing what we've concluded so far, which is that if you have a variable that you're trying to copy from one variable, like a value you're copying from one object, a source, to some other destination object, and you're trying to figure out, is it safe to replace the copy with the move? It all boils down to, is the source for the copy operation an L-value expression or R-value expression? If it's an L-value expression, it's not categorically safe to replace the copy with the move. The compiler will never do it because it might not be safe. In some cases where we know specifically more knowledge about the code, we might be able to say, well, it is safe, and then we can override the default type system with std move. In the case it's an R-value expression, then it's always safe to replace a copy with a move, so the compiler will do this. And effectively, it'd be really nice if the compiler just automatically did this for us, so we don't have to say move, move, move all over the place. If it's safe to do, the compiler just automatically does it, and this is how the language is defined. And effectively, the language is defined in such a way that when you're trying to propagate the value of an object from one object to another, a move operation, that's basically what I'm referring to as this last bullet here, a move operation will be performed if such an operation is available, and the thing that you're moving from, the source for the move operation, the source from this operation where you're propagating values, is an R-value expression. So like it all boils down to whether or not something is an R value. This is why it becomes very important if you're trying to understand copying and moving. It's really quite essential that you understand the difference between L values and R values. Otherwise, you can never tell like what's happening here. Is it copying? Is it moving? I don't know. So it's unfortunate. It's kind of complicated to understand these things, admittedly, but it is quite essential when you start to get concerned about very efficient code. I just want to come back to the word available. Like, why does it say if such an operation is available? Well, it might not be available. In other words, maybe you have an R value expression that's the source for the copy operation that you're doing, and if the compiler is saying, is it safe to replace it with a move? And it goes, R value expression, yes, we're good to go. Well, maybe there is no move constructor, move assignment operator. It's a user-defined type. Maybe you didn't have to define a move constructor, move assignment operator, so maybe there isn't one available. In which case, instead of a compiler error and going, oh, you can't do this, instead it will just silently fall back on doing a copy. So the other, maybe more subtle reason why such a function might not be available is maybe you have a move and copy, or move constructor, move assignment operator, but maybe the R value expression is a constant expression, or like maybe I should say this differently. It's a non-modifiable expression. Like in other words, the R value expression is referring to an object, and the object's const. So you can't modify it. I want to be careful not to say constant expression because I'm not talking about const expert, but like you have an object that you can't mutate because it's const. In this case, again, instead of getting a compiler and saying, oh my God, I want to move, but I can't, instead it will just silently fall back on a copy. So this is what's meant by available. Like the compiler will look at the expression you're trying to propagate the value from, the source, the propagation operation. It will say, is it an R value? If it is, well, we'll try to use a move if there's one available, but there might not be for the reasons that I just mentioned. Otherwise, it will fall back on a copy. But it won't give an error and say, I want to do a copy, I really want to, there isn't, or I want to do a move really badly, there isn't a way to do a move, error. It won't do that. Instead, it just silently falls back on a copy, which is probably the behavior you would want. Otherwise, you get lots of compile errors for kind of very bogus reasons. Mm-hmm.
Is there like any way to force an error in that case, or maybe in specific cases like flags or something?
Well. I'm trying to think about, is there any weird way you can do things? I mean, generally no. Maybe in some special cases you might be able to do something weird with, but generally no. But you wouldn't really want it to issue a warning because I guess the only situation you might care about is maybe you think it's moving, but really it's copying because you didn't kind of look carefully at the code. You just said, like, what could possibly go wrong? And then it's silently doing a much more expensive operation. And there are situations where accidentally you might, without knowing it, prevent a move from happening. And so it's not like what you're suggesting would not be without merit, that you might not be interested in it. But I can't really think of a mechanism, at least off the top of my head, for being able to do that in a general case. And I don't know of any compiler that has warnings for that. Although you never know. They're always adding better warnings all the time. So it's quite possible they could add something like that.
Mm-hmm. I think the first assignment I had all my members variables and const, and then it deleted the move operator for me automatically.
Right.
It failed when I tried to manually call them.
Yeah, but I guess the situation that maybe we're concerned with, like you're getting flagged with an error, right? But I think the issue that the student was talking about was more like it works, it compiles, but what's happening is because there was no move constructor, move assignment operator, secretly without you realizing it, it's actually doing a copy. And maybe for that type, the copy is much more expensive than a move. Like, would there be a way to prevent that? anyway, I'm getting maybe a little bit off track. I don't want to I mean, yeah. Anyway, yeah, but you're talking about something a little bit different. Like you were getting a compiler error because it had no choice but to move. Like it was really wanting to move for some particular reason, but it couldn't move because the move constructor, I think it was deleted because of what you're doing.
It was trying to be called, but there was no move on it because it was been deleted automatically by the compiler.
Right. Yeah. Do you want to see anything else here? I think that's everything for this slide. Any questions? Okay. So maybe just one code example to kind of tie together like all the things that we've been talking about so far. So this is going to be putting together quite a lot of stuff. But what I have here is some example code in the middle. And what we want to do is kind of walk through and identify like where a copy is happening versus moving. There's a whole bunch of places where we're propagating values of variables from some source to some destination. And for each one, we want to look at it and say like, what's going to happen here? Is it going to do a copy or is it going to do a move? I added this comment. I think this comment wasn't in the original slides that you have. I just wanted to point out because, I mean, I never formally introduced std string in this course, so some people might not be familiar with it. It does define a move assignment operator and a move constructor and a copy assignment operator and a copy constructor. So basically it has move operations defined as well as copy, because this could impact some of the conclusions we make below. You know, does it move? Well, if it doesn't have a move operation defined, you know it's not going to move because it can't. So it does have move and copy operations defined. So we have a function called getValue. It returns by value and it returns a string, std string. We have another function called getConstValue, which returns a const string. Don't ever do this in your code. Don't ever, if you're returning by value, never const qualify the return type. As I mentioned earlier in the course, if it's a built-in type, like if this is int, the compiler will just ignore it. It's sort of like a more benign sort of issue. But if it's a user-defined type like what we have here, the compiler will say it's const. And basically, if you do this, as we'll see in a moment, this completely makes moves impossible because you can't move from something that's constant. Anyway, but we'll see this as we go through. So let's start with this function here. And basically, we're going to walk through line by line. And there's a whole bunch of things that are propagating values of variables from some source to destination. And we want to identify which ones are copying versus which ones are moving. So we look at this first example here. So we have this string s. And the constructor parameter that we're passing is the return value from getValue. So what we want to do is we want to look at getValue, look at what type it returns here. It returns a std string. It's returning by value. So what is this? What type of expression is this thing that we're initializing from, the source for our copy or move? In other words, get underscore value bracket bracket is an L value or an R value. Functions that return by value are what? This is like one of the most important examples, perhaps, of the particular type of thing that this answer is. L value or R value. Okay, more specifically, it's a pure R value. But for the purposes of move versus copying, I mean, it's great if you can split hairs even further and say pure R value. But for the purpose of moving versus copying, all we care about is an L value versus an R value, which includes both pure R values and X values. So anyway, this is an even better answer that you gave. So basically, as a consequence of this being a pure R value, it's also by definition an R value expression. So because of this, it can move. It turns out that for reasons that we haven't talked about yet, which is one of the reasons why we need to talk about this, actually nothing happens here at all. The compiler is required to elide the move. In other words, elide is just a fancy word for omit or whatever. Like it can essentially optimize out the move, and furthermore, it's required to do it. So we'll come back to this later, but just ignore this copy elision that's happening here. If it didn't do this, then what would happen is it would move, because this is an R value expression. We'll come back later when we talk about copy elision and see why it is that it's actually not doing anything here. Again, this is the holy grail. Like you don't copy, you don't move, you don't do anything. Like you can't be doing nothing. No CPU instructions, 0 time that it takes to execute. Anyway, but it would move if there wasn't copy elision involved. And since we haven't been introduced to that, we'll kind of work through this on the assumption that there is no copy elision happening. Next example here. So S is what type of expression? L value or R value? Okay, it's because it's a named object. Any named object, like things that are named typically are L values. So this is an L value expression. So because this is an L value, is it going to copy or move? Essentially, it needs to choose between a copy constructor and move constructor. Well, I guess you can read as well. It's doing copy construction here. So it's going to do a copy. But the important point is that this is an L value expression. So if you go on to this next case here, this is going to be choosing, like we're constructing an object use, so it has to choose between copy construction versus move construction. So what's going to happen here, the compiler will look at the expression that we have here, std move of t. Std move of t is a what? R value or L value? Yeah, it's an R value expression. More specifically, it's an X value, but for the purposes of this discussion, it's sufficient just to recognize it as an R value expression. So because of this, it's going to do a move. Here, now we have a bunch of assignment operations here. So we're trying to assign S to T. So basically the compiler is choosing between, do I do a copy assignment versus a move assignment? Do I do copy or move here? In this particular case, again, S is an L value expression. So L value expression is going to result in a copy. The source for the copy operation, or the source for the propagating the variable from the source to the destination. Our source here is the L value, so it will do a copy. The next line here, we have std string of hello. So this is going to correspond to a temporary object. I mean, I guess this would be like an X value. Well, it's probably better to just call it R value, because then we don't have to split hairs here. The expression std string hello is an R value expression. It basically corresponds to a temporary object that's produced by invoking the string constructor with this parameter hello. So because this is a R value expression, this is going to result in a move. It will basically rip the guts out of the string probably and stick the allocated memory into T that holds the string value. That's most likely how it would be implemented. Here we have a std move, which kind of gives away that probably it's going to do a move. But the reason why it doesn't move is that std move of T is a R value expression. So R value expression will result in a move. And then this last line here, this is what I was alluding to up above here, saying warning, this is a bad idea. This is why it's a bad idea. If you have a function that returns by value, never const qualify the return type. The reason why, if you do this, you make it impossible for a move to ever happen. So if we ignore the const and just kind of blissfully follow the pattern that we're doing for everything else here, we would look at this, we go const value bracket bracket, or const value paren. This is the return value of a function that returns a std string. If we ignore the const, which we can't really do, but if we ignore the const, we say, well, this expression here is an R value expression, and actually the const doesn't change this. It's still an R value expression no matter what. But then the compiler says, well, can I do a move or copy here? So it would say, well, I'm inclined to do a move. It's an R value expression. It's safe to do a move, but it can't. The reason that it can't is that if it tries to move from this thing, it probably needs to modify that thing, but it can't modify it because you said the return value is const. It's kind of crazy, right? Like you're returning a value back to the caller. The variable is kind of theirs, right? Like you have no right to make dibs on the value that you return. You're returning it for the purpose of the person who's calling you to use it, but you're saying, haha, it's const, you can't change it. Like the thing I'm returning, you can't change it. Like there's not any reasonable reason why you would ever want to do this, right? But occasionally in code, I see people sometimes do this. Like maybe they don't know how to use const properly, and then occasionally you'll see const creeping into the return type. For non-reference types, return types, it doesn't make sense. If you're returning a reference, it's different because then the const is referring to the referee of the type, the thing that's being returned, like the referee of the reference. But here we're talking about just the actual value itself, whether it's const or not. And it never really makes sense to const qualify things because of this reason. You're basically saying you'll never be able to do a move here. And why would you do that? And yeah, I guess I'll probably stop here because there's not really time to get into copy elision. But the next thing that we're going to be talking about, copy elision. So basically what we'll be doing is kind of coming back to this particular line here, line 8, and we'll be learning why is it that there's not actually any move or copy here. It's completely elided altogether.